Here we're going to look at a very straightforward example of a line in three-dimensional space. Basically, all we're being asked to do is find the equation of a line that goes through a certain point and has a certain direction vector in three-dimensional space. And if you remember, those are the two things that you need to write an equation in three-dimensional space. So let me remind you what that formula looks like. So lines in space we write typically as a set of parametric equations, which are something we studied a lot back in Calc 2, where the x, the y, and the z are defined independently in terms of a parameter t. And so as t changes, you get different x, y, z points. And as t ranges over all values from minus infinity to infinity, it sketches out the line, that collection of x, y, z points. So here, x naught, y naught, z naught is the point that your line goes through, and then the A, the B, and the C is the direction vector for the line. So this is A, this is B, this is C. And in fact, if it helps you, when you have an example like this, you can even write, x naught, y naught, z naught on your paper, A, B, and C, just to help you remember what goes where. All right, but once we have those identified, it's very straightforward. Just plug and chug is all it is. So we have x, we have y, we have an equation for z. So the x would be x naught plus at, so negative 4 plus 2t. The y would be y naught, which is 0, plus bt, so negative 1 times t. And then the z would be z naught plus ct, so 5 plus 5/3 t. All right, and that's it. This is more or less our answer right here. All right, now one thing I want to mention before we close out this video is I want to mention something about this direction vector here. This direction vector, there's nothing special about him. It just needs to point in that direction. It could be a unit vector, it could be twice that length, 3 times that length. It doesn't matter what direction vector you use for your A, your B, and your C, as long as it goes in this direction. When you sketch out the line, depending on what scalar multiple of V you use, it might sketch out the line faster or slower, but at the end of the day, it's going to be the same line. Now, why do I care? Like, what's the point of mentioning that to you? Well, look at this vector here, 2, negative 1, 5/3. Wouldn't it look a lot better if this wasn't a fraction? So what we can do is we can actually triple this vector. We just multiply it through by a scalar of 3. It'll be 3 times longer than it currently is, but that's okay. It's still in the same direction. So if we called that new vector, I'll just make up a name, we'll call it W. That'll be the vector 6, negative 3, 5. Well, if I can write correctly, 6, negative 3, 5. 3 times 2, 3 times negative 1, 3 times 5/3. This guy doesn't have any fractions, so you could write your set of parametric equations as x equals negative 4 plus 6t, y equals negative 3t, and z equals 5 plus 5t. And to me, that just looks a little cleaner. I think you would agree, because it doesn't have this ugly fraction here. And these actually represent the same three-dimensional line. And again, the only subtle difference is as you graph these guys, one will be graphed faster than another. But again, that doesn't change what the line is. The line would actually be the same thing.